In the next set of videos, we're going to look at classifying material as ferromagnetic, paramagnetic, diamagnetic. So since we are in higher grades, we will have to use fancier words, a better way to define those materials. And that's what we are learning in this video. Terms that describes magnetic property of material. So this is the list, overall list. So first we have the cause, the source, magnetizing field. Then how strong it is, that is magnetizing field intensity. Then the effect of it. So this two, or that's one and the same actually. So what is the effect of such a thing? That's what we are calling it as intensity of magnetization. Then we have how permissible a material is. That is how much magnetic field line will it allow. That is your magnetic permeability. Then we have relative permeability. That is to compare with vacuum. And magnetic susceptibility. How easily can a material get magnetized? This is an overview of things. If you guys want to pause and have a look or write it off, you can write it off. So let's start off with second point, magnetic field intensity. Magnetizing field by default is the source. It's just telling, okay, this is the cause, nothing else. That's the term used. Magnetizing field intensity, that has to be dealt with in detail. So this is the cause. It's, if not, you can describe it as the, somewhere I have written, ability of the magnetizing field to magnetize a material medium placed within it. It's about the strength. I have written over here. Represented with H, and it's defined as its magnitude can be defined as the number of ampere turns flowing around the unit length of solenoid required to produce the given magnetizing field. Okay, so basically we are going with the synonym or making use of solenoid to talk about all of this. I hope it made sense. We're making use of solenoid to talk about the magnetizing aspect of things. Okay, let's look at the math. So we have H, which is equal to Ni. So here N is your number of turns or number of turns per unit length, not or actually. It is per unit length. And in terms of the magnetic field strength and all of that, so we know that V naught is equal to mu naught Ni. So here we have Ni, and if you rearrange a bit, you get V naught by mu naught, right? Yes. So this is nothing but mu naught H. A bit of rearrangement, and we get this. The fastest way to get the SI unit is through this formula. N is your per length, right? Number of turns per length. So that will be M to the power of -1. And current unit is your ampere. So ampere per meter. Okay, so that's the fastest way to get the SI unit. Now the effect. That is the cause. H is the cause, M is the effect. So there are two ways to define it. The first way is it's the magnetic moment per unit volume of the material. It indicates how strong a material is magnetized in presence to an external magnetic field. So that's one of the ways of talking about it. Right? So if you're not understood this, it's nothing but how actually this will be understood better when you're seeing the different materials. When you're talking about ferromagnetic material and all of that, you get a clear picture of what this means. By now you should know this, but if you're not able to, we'll understand it a lot better in those section of videos. So mathematically, how does it look like? So what is the magnetic moment? What is the symbol? At least try to recall the symbol. Is small m. Since it's defined as per volume, so we have a different symbolic representation over here. Capital M is equal to small m by V. So when I substitute m over here, so we have N, Nm, A by length into area. But length here is 1, because it's per unit, right? And if I make it as per unit length per meter, E and A can get cancelled. For L is equal to 1 meter. So what do we have? We have M is equal to Nm. Here M is nothing but surface magnetization current set up in a solenoid of cross section A having N turns per unit length. So that's why we have taken L to be 1 meter. Okay guys. So we know that M is equal to Nim because we have it to be of unit length and all of that. So it would be so. And we have, sorry, capital M. And we have, we'll express in terms of Bm. Okay. Bm, which is equal to mu naught Nim. This is your, where, I didn't put that, sorry. Where Bm, my pen is acting up again. Induce magnetic field. Okay. Please don't mind, my device is not, this is some glitch. So let me come back to this again. Sorry, we're looking at the effect of it. So one of the ways of talking about the effect is magnetic moment. How many atoms per se are oriented in the direction of magnet, the external magnet? Okay, that does it make sense? So that's how it becomes a magnet, right? Whenever you get a ferromagnetic material near a magnet, it too becomes a magnet in some sort. That's what you're trying to talk about. How does it become? It will start orienting. The magnetic moment, it starts orienting in one particular way. And that's how we can make it. And when we substitute all of this, we get M is equal to Nim. Nim, sorry. But the induced magnetic field is given by this formula again. Okay, same funda, same thing everywhere. Instead of I naught or I, it's Im. The same formula, it's not no different, but the cause is different, the place is different. Okay, so we have M will be equal to mu naught M capital, sorry, Bm is equal to, my bad, mu naught M, therefore M is equal to Bm by M naught. Don't worry, you'll understand this better here itself. There's one more definition and we'll be able to explain that better. One more way of talking about is pole strength. How strong the magnetic field is. End to end, you do that, divide by the cross-sectional area and all of that. You get your result in that way also. So basically, your capital M is equal to Qm into 2L. That's your dipole moment divided by your volume, right? So this is, let me write that. Your dipole, magnetic dipole. Just a second, let me rewrite this. Dipole magnetic divided by volume. So 2L gets cancelled. We have Qm by A. Here too the unit is same. We have ampere per meter. Okay, let me sum it up. So you have a cause, you have a material placed in an external magnetic field. Okay. Now, end of it, you have a magnetic field because of the external magnetic field P naught, and within the material, say solenoid. Within the solenoid, if there is an ferromagnetic material, within that there will be extra bit of magnetic field. As a whole, what happens? The material becomes a very strong magnet. Actually, let me show this. I have the perfect video for this. Okay, guys, I have it here for you guys. Now, so the video starts off with no current, a solenoid, and a compass that's pointing to north, no current. Now there is a current flow and there's certain deflection. Can you see that? Observe it. Observe the deflection. Current is 125, that is microampere or something like that, milliampere or microampere. Okay. So this is nothing but your magnetic field intensity, something to do with H. Now, something happens. In a second, something happens. Current is the same. Please look at the current. It's the same. So what is that I'm doing? I'm keeping a something called a soft iron. So you can see the deflection, right? You can see how it changed. Can you see that? See the amount of deflection? It's a bigger deflection. So current is the same. I switched off the current. So you can see that, right? Presence of a material, something like this, okay? That created a stronger magnet. This is your BM, M and all of this. So basically this two scenario talks about a set of wire, wrapped up around a soft magnet. Set of wire is your solenoid and this is your soft iron, right? As a whole, yeah, solenoid is what we are talking about. The wires, they themselves give what? B naught. The materials give Bm. So the total, therefore the total magnetic field inside, I think I have written that total field inside a magnetic field material, I have already written that, will be what? This was a good video. B is equal to B naught plus Bm. So all in all, this is B naught is your mu naught H, Bm is your mu naught M. So basically mu naught H plus M. Again, this is just commonsensical and you saw this practically also, right? So it's just in the form of a formula. That's it. Okay. So you have to write everything. There's no option.